Hey, thank you, everyone. It is my great pleasure to introduce my colleague, collaborator, and friend, Jason Kawasaki, to our CIQM seminar today. So Jason started off at Princeton, where he was an undergraduate, before moving to do his PhD studies at UCSB in the group of Chris Palmstrom. Jason then moved to Cornell as a Kavali Fellow in the group of Daryl Schlom and Kyle Shen, before starting his own independent research group at the University of Wisconsin-Madison. I know this is kind of a cliche to say that Jason has won every single prize out there. I know that's said every time, but truly Jason has won every single award from grad school throughout his career in Wisconsin, and has really done quite phenomenal work, particularly in this area of using MBE to make new Heusler materials. So thank you very much, Jason, for joining us virtually today, and I'm really looking forward to your seminar.
Great. Thank you, Julia, and thank you to the organizers for providing this great venue. So what I'll do today is I'll share some of our thoughts and outlook on what we've been doing with Heusler compounds, and in particular, thinking about new ways to synthesize high quality quantum materials and put them under some very interesting strain geometries to reveal new properties that are not possible in bulk crystals or conventional epitaxial films. And I'll start the story by saying a little bit about the fact that strain is a really powerful tuning knob for either tuning or unleashing new properties in quantum materials. And I'm just showing a few of the highlights that I'm aware of. So as one example, it's possible to use strain to induce superconductivity in certain kinds of crystals. And here's an example of a thin film of ruthenium dioxide. So ruthenium dioxide in single crystalline form is just sort of a boring old metal, as you can see in this resistivity versus temperature curve in red. But if you grow it on the right kind of substrate to impart epitaxial strain, the group of Kyle Shen has shown that you can actually turn ruthenium dioxide into a superconductor. There's also longstanding interest and great demonstrations of using strain to tune properties of light, such as ferroelectricity. So I'm highlighting here some of the work of Daryl Schlom's group a number of years back. And there's also great new examples of using strain to essentially tune or turn on and off topological states in various kinds of topological semimetals. So here's the example of ARPAS spectra, where by applying in its unstrained state, you can see these topological states that are crossing through the Fermi energy. And by applying about 2.4% strain to one of these crystals, you can basically tune the topological states off. And the typical ways in which we strain materials are pretty simple. One is you take a bulk crystal and you just pull on it, okay? And so that's what's been done in this tantalum selenide picture. And another way, which is highly controlled, is you grow a thin film on top of a substrate. And you use that substrate to impose an epitaxial constraint to the film that's been grown on top. Okay, so there's certainly been great success in using epitaxial films to impart strain onto a substrate and reveal new properties that don't exist in the bulk. But I have to say that there are certain limitations to what one can do by epitaxy, in the sense that epitaxial strain is typically static and it's discrete. Typically, when we want to impart strain on a substrate by epitaxy, we're limited to particular combinations of film and substrate that have a certain percent lattice mismatch. So you can't really do this in a continuous fashion. And also, it's basically you're stuck with one strain state after you grow that sample. So it's a little bit more limited if you want to maybe say tune some dynamic property or with a dynamic or time varying strain. Another limitation is that there are elastic limits to how much strain you can impart in a crystal before it will plastically deform. And we think about this in terms of critical thickness limits. Okay, and typically for a thin film on a substrate, that critical typically, you can't apply more than 2 or 3% strain. That's really pushing it. And there are limits to how thick you can grow that sort of film. Now, let me give you a thought experiment. What if you could make a high quality single crystalline membrane? With that membrane, there's a lot more flexibility in what in the strain states you can apply. So for one, flexible membranes you can tune dynamically, right? You're not locked in place by a particular substrate. And also, you can apply strain in more complex geometries than what you could apply in a conventional epitaxial film. So one example is thinking about simple things like doing a bend or introducing strain gradients inside a material. And then you can ask the question, well, what kinds of new properties might you expect if you could strain in new complex geometries and in higher strain states than what you can access in a conventional epitaxial geometry? So one example property is flexomagnetism, right? So we all know that magnetism is highly sensitive to local bond lengths, in other words, strain, right? And it's been widely employed that these linear couplings, we call this piezomagnetism. There's a coupling to the strain term squared that's called magnetostriction. These are commonly used today to make magnetic actuators. But it turns out that in principle, one could have a response that relates to the gradient of the strain. This term would be called flexomagnetism. There's an analogous term in ferroelectricity called flexoelectricity. And I would say that this sort of property, this coupling has been predicted, but it's been very hard to experimentally demonstrate this coupling because it's very hard in conventional geometries to actually control a strain gradient. So there's a long history of actually making some high quality membrane materials. I'm showing some examples of here. On the left, there's a very long, nice history of making semiconductor membranes like silicon germanium or 3,5 semiconductors like gallium arsenide. And there's been some great work from my colleague here at Wisconsin, Max Legali, in doing this, and they can make some nice, pretty complicated membrane shapes that are sort of twisted and rolled up. There's also great work historically that's been coming out of the Rogers Group at Illinois and now Northwestern. And more recently, some of the quantum materials community has also taken on to similar techniques. So the group of Harold Huang has been looking at complex oxide membranes, and they show that by growing these manganites and releasing them in single crystalline form, by applying strain to these membranes, they can induce things like metal insulator transitions. And they've also shown that in membrane form, you can apply much higher strain states than what you can access in an epitaxial crystal. So they showed here data up to 5% strain states. They've shown that you can even go to 8% strain. So this is much larger than what is typically thought of as the limits of conventional epitaxy, where you can only get to about 2 or 3%. Okay, so these approaches are quite powerful and they're great, but they only work in specific material systems. So I'd say that in both this sort of silicon germanium case and in this complex oxide case, the strategy is you grow a thin film on top of a sacrificial buffer layer, and you etch away that sacrificial buffer layer to release some sort of freestanding membrane. In this LCMO case, it's this strontium calcium aluminum oxide buffer layer that you can just dunk in water. And that's how they make these membranes. And that's great for material systems where you know the etch chemistry really well. But there are lots of other interesting materials out there for which we may not know the specific etch chemistries, or materials that, let's say, are perhaps more air or water or solvent sensitive, where you can't find a possible etch chemistry that would allow you to release this sort of material. So what do you do in those cases? How can we apply this great concept of interesting strain states and this enhanced tunability to other kinds of materials for which the etch chemistry is not so favorable? And the approach we've been taking is to borrow ideas based on remote epitaxy. So remote epitaxy is this concept that was brought up by Jiwon Kim's group a few years back. And what they showed is that if you take a single crystalline substrate and put a layer of graphene on top, they show that you can grow a single crystalline film on top of that that has atomic registry or epitaxial registry to the underlying gallium arsenide substrate. And you can see this pretty nicely in this cross-sectional STEM image. Okay, it's growing almost as if the graphene were transparent or growing by remote interactions, and that's why they coined this sort of growth mode as remote epitaxy. So after seeing this concept, we asked ourselves the question, well, can you apply it to other materials? Can you go beyond conventional 3,5 semiconductors and apply a similar concept to more complex quantum materials like Heusler compounds or like complex oxides, if you can do so due to the weak film substrate interactions between, say, the Heusler layer and the graphene layer, you'd expect that you might be able to mechanically exfoliate freestanding membranes. Okay, and that's the original goal of this talk. Another outcome of this sort of approach is that is to utilize the fact that graphene is quite an excellent solid state diffusion barrier. So one of the long-standing challenges of Heuslers is that these particular materials are really great ferromagnets and half metallic ferromagnets, and they're nice and lattice matched to 3,5 semiconductors. So they're a great materials platform for realizing a lot of the device concepts for spin injection based devices. And one of the major challenges is that these interfaces are inherently stable. And so one thing that graphene brings is that it's a great solid state diffusion barrier that's been known for years. So it could block interdiffusion or ion transport across the interface. But ideally, because graphene is atomically thin and transport occurs via tunneling across that interface, this is a limit where this atomically thin diffusion barrier might be nominally quasi-transparent to the injections of charges and spins across this interface. So we think that this graphene-based approach might also be a solution to the long-standing challenges of stability and interface control across interfaces that are otherwise chemically incompatible. And to flesh this out a little bit more, the particular system that we're interested in doing this with is these Heusler compounds. So Heusler compounds are ternary intermetallic compounds that consist of two transition metals on this X and Y site in red and blue, and a P block metal, this green site on the Z site. And you can think of this material as essentially a stuffed zinc blende lattice. So if you look at the lattice that's given by the red and the green atoms, that makes the zinc blende structure. That's the same structure that you would find for gallium arsenide, or if you call it diamond, silicon or germanium, right? And you just stuff this additional blue atom at these half zero zero positions. And by stuffing this additional atom in the lattice and finding that there are compositions that contain many transition metals, this opens the door to lots of interesting properties that you do not observe in 3,5 semiconductors. So I just list sort of a library, some of these properties. A lot of early interests were in the magnetic properties. In fact, the first half metallic ferromagnets were found among this Heusler class. And since then, there's been a whole range of other properties of interest to find in these materials. An additional interest in these materials is that I told you that it shares a very close symmetry match to 3,5 semiconductors. One of the sublattices is also zinc blende. So it is also possible to grow these materials directly on technologically important 3,5 semiconductors. So the grand goal of my group has been to understand how to control these interfaces to make Heusler-based devices on a 3,5 semiconductor platform. And we think graphene can be a nice solution to some of the chemical incompatibility problems. But also, if we have this graphene, we have a platform for now mechanically exfoliating membranes and revealing hidden properties via strain that you can't access in materials that are in conventional epitaxial forms or single crystalline bulk crystal forms. Okay, so what I'll tell you about today is some of our work in several of these directions, all motivated by what can you do now that you sort of know how to grow films on graphene. Okay, so in the first part of this talk, I'll tell you about the original motivation we had, which was which will be our finding that we can induce magnetism in these Heusler membranes via a coupling to the strain gradients. Or in other words, we think we have the first experimental demonstrations of flexomagnetism by using these high quality single crystalline membranes. In the second part of the talk, I'll try to pose the question, how does this remote epitaxy concept actually work? Is the growth dominated by remote interactions between the film and substrate that permeate through graphene as if the graphene is transparent, or could defects in the graphene play a strong role? And I'll try to give you our evidence that we think that in most cases, it's the defects that actually win, and the growth mode can be more accurately described as a seeded lateral epitaxy mode. And then finally, I'll give you an outlook and some preliminary data on this idea of using graphene as a properties-selective diffusion barrier, where we're going to quantify exactly how well does graphene perform as a diffusion barrier and give some insight on the prospects for the charge and spin transport across the interface. Okay, so first off, I'll tell you about this flexomagnetism in rippled Heuslers membranes. And this is all the work that's driven by my very talented student, Dongshui Du, who's about to graduate this spring. Okay, so the basic concept that we're going to employ is based upon this remote epitaxy idea. And so what we've done is we'll transfer a monolayer of graphene onto a sapphire substrate. And we pick that sapphire substrate because it has a reasonably close symmetry and lattice match to the gadolinium platinum antimony membrane that we're interested in growing. So this material becomes antiferromagnetic at with a nail temperature of about 11 Kelvin. And most of our measurements, we're gonna ask the question, how can we tune the magnetism if we can make a freestanding membrane? And again, we can make a freestanding membrane by because of the fact that there's graphene here. Okay, so we've shown that we can grow single crystalline films of gadolinium platinum antimony on top of this sapphire substrate. I'll demonstrate this preliminarily with some electron diffraction patterns. So here's an electron diffraction pattern of the graphene on top of the sapphire right here before we grow in this Heusler film. And here's the electron diffraction pattern of the film after we've grown on top of the graphene. These very, very extended streaks indicate that we have sort of an atomically stepped surface. And the way that we make these samples is by molecular beam epitaxy. So this is an ultra high vacuum deposition technique where we place a sample in vacuum conditions that are very, very clean. We load high purity source materials inside these furnaces, and we sublimate these source materials onto a heated stage. So in sort of CAD view cross section, it looks like this. And while we're growing the film, we can monitor the crystal quality of the surface using electron diffraction tools at grazing incidence that makes it very sensitive to the sample surface. If you just zoom in, this is sort of a cartoon version of what this process looks like. And you can think of it nearly in its most ideal form as something like atomic spray painting with atoms. So we have these controlled shutters, and basically we can open and close exposures to these atomic or molecular beams and control the stacking sequence in the most ideal way, hopefully, by opening and closing the shutters in some pre-programmed way. Okay, so back to the particular crystal that we grew. Again, it was a sapphire substrate with graphene in the middle, and then gadolinium platinum antimony on top. Here's a cross-sectional TEM image of that particular sample, showing that we do have sort of epitaxial registry across this interface. I will note that sort of this sort of blurry region right here in white at sort of a middle color range, this is where we expect the graphene to be. It ends up being pretty challenging to get nice atomic registry across this interface. We think that's because these samples actually exfoliate quite easly. Okay, it could also be because we're looking through some finite thickness and multiple atomic columns. So there might be some steps that we're basically projecting through in this image. But in any case, so we can verify by electron microscopy that these films are epitaxial. We can further verify by X-ray diffraction that we have something that is single crystalline. Let me close my Slack message. Okay, so by X-ray diffraction in a sort of theta to theta scan in the out of plane direction, we can show that we have the expected sort of 1-1-1 oriented film, and then we have these additional very, very bright substrate reflections. We can then basically adhere this membrane to crystal bonds and then mechanically exfoliate it away. And so here's a picture of that exfoliation. So here is this membrane that's adhered to crystal bond, and we've exfoliated it from the substrate right here. In this particular case, the graphene only occupied this square in the very, very center of this sample. The full dimensions of the sample are about 1 by 1 centimeter. So the dimensions of the graphene that we had in the middle were on the order of about 7 by 7 millimeters. And exactly the locations in which the graphene was, that's where we can exfoliate the sample. Okay, so we can pop this exfoliated membrane back in the diffractometer, we can measure it, and we can confirm that we have exfoliated a single crystalline membrane in blue that no longer has any of the peaks associated with the substrate. Okay, so that's exfoliation. We've shown we can grow single crystal membranes on graphene. The graphene allows us to decouple, we can make membranes. And now once we have these membranes, we can subject them to very interesting strain geometries. And one of the geometries we're very interested in is ripples, because they have lots of this strong gradient term in the strain. So a simple way of fabricating, inducing ripples in these membranes is that if you attach the membrane to a polymer at some elevated temperature, and you cool that polymer down, because of the thermal expansion mismatch, you'll actually form ripples into that membrane. And so here are some optical micrographs of ripples that are formed in this membrane. Typical lateral periodicities are on the order of tens of microns. And if you do atomic force microscopy of these rippled membranes, you can also measure the typical ripple heights, which would be on in the level of sort of single digit microns. And if you choose different polymers with different thermal expansion coefficients, we can actually change the degree of rippling, or in other words, the aspect ratio between the height and the lateral periodicity of the ripples. So now let's do some measurements. What is the ripple actually going to do to the properties of this membrane? So let's do a magnetic measurement. So if you take one of these samples that's grown directly on a film, so let's just call it a film. You grow it thick enough so that it's unstrained, and you measure by squid M versus H, you'll find this nice linear relationship at room temperature, and the material is paramagnetic as expected. If you go a little, hold on a sec, let me close that. Okay. What we can now do is we can compare this measurement with that of a rippled membrane that we exfoliated. Okay, so if we take this sample and we now exfoliate it, and then we put ripples in it by sticking it on this polymer, with a small degree of rippling, what you'll notice is that we open up a hysteresis loop indicative of ferro or ferrimagnetism. And if you stick it on a different polymer with a larger thermal expansion mismatch and even more ripples, we find that the saturation magnetization increases quite dramatically. And again, it scales with this aspect ratio of the ripples. So now you can ask the question, well, if we investigate this a little bit further, what's causing this? So if you remember from this expansion, there can be a coupling between magnetism and strain terms, either the strain or the strain squared, right? So, or there can be a strain gradient term. So if we look and take some estimates of how large is the strain in our particular ripple geometry, based upon the thickness and the height and width of our ripples, we estimate the strain state, maximum peak values of strain are only about 0.15%. And they're highly concentrated basically at the peaks and valleys of this ripple structure. If you then do a simple DFT calculation and ask what is the magnetic state as a function of homogeneous strain, what you would find is that at this 0.15%, the ground state would actually be antiferromagnetic, and it actually, with homogeneous strain, requires something on the order of 5% strain to tune this material into a ferrimagnet. So based upon these sort of estimates, we think that these couplings to strain directly, strain or strain squared, are not strong enough to explain the observed hysteresis loops we observe. And we think that the most likely, the term that dominates in our particular case is the strain gradient term. And therefore, if true, if fully borne out, this would be the first experimental demonstration of flexomagnetism. So there's a lot of more work to be done in this regard. This is sort of a first level observation, but ongoing work in my group is really aimed at really quantifying what is the true strain state of this particular material in a ripple geometry with some microscopy, and actually mapping out the magnetic order at very small length scales. So if I have a chance to come back at some point post-COVID, hopefully I can tell you a little bit more, a more quantitative understanding about the origins of this ripple-induced magnetism. But in any case, magnetism is just one of only a handful, only one of many properties that you can envision tuning in this membrane geometry. So these Heusler materials not only show interesting magnetic properties, but also very interesting topological and novel superconducting properties. I focus mostly on what we can do via interesting strain states that you can access via bulk by doing ripples. In the future, one could imagine accessing even higher strain states. But if you can make single crystalline membranes, there's also now the possibility of playing games with layer stacking and tuning twist angles in the similar way that people are now making tremendous progress in 2D materials and tuning interlayer twists. There's also greater possibility for tuning properties of materials by coupling it with other materials that have large first order phase transitions. So for example, making heterostructures of these released membranes where it's grown on top of a shape memory alloy. So I think this is really just the beginning of what can be done now that we have this platform for making exfoliatable high quality single crystalline high quality single crystalline membranes of Heusler compounds. Okay. So second part of this talk, now that I've shown you that this growth on graphene approach is really powerful, there's some interesting physics we can explore. Let me take a little step back and give you our view of how this epitaxy process actually works. What are the atomic scale growth mechanisms for growth on graphene? Okay, the first order claim when the first papers came out was that the growth occurs via remote interactions that essentially permeate through this graphene as if the graphene were transparent. Okay, but let me pose the question, well, what if the graphene isn't perfect? What if there are defects in the graphene such as pinholes? Could there be some defect-induced process, for example, something like a seeded lateral overgrowth that defines this growth mechanism? And I'll give you our evidence that I think that in most cases, this is the mechanism that actually dominates. Okay, so to put this on a little stronger footing, let me tell you a bit about more so the basis for this argument for remote epitaxy. And this is based largely on model calculations where they ask the question, let's say you have some crystalline substrate and you put a layer of graphene on top. You can do a DFT calculation and ask the question, how large is the lattice potential of the substrate that permeates through graphene at some height about 3 angstrom above the surface? So this would be sort of the lattice potential that an atom would feel if it were deposited on top. And is it strong enough to seed epitaxy? So if you do that calculation on sort of a perfect slab at the DFT level, you would find that for certain crystals, yes, there is a potential fluctuation that you would expect. And this is the fluctuation of the substrate lattice potential through graphene. For gallium nitride and for materials with high polar bonding, you get sort of larger magnitudes. And for materials that have high non-polar bonding, these fluctuations are essentially zero. So there is some potential fluctuation, but if you look at sort of the magnitudes here, gallium nitride is a highly polar case. This potential fluctuation is about 40 millielectron volts. And if you compare that to typical values of KT at a growth temperature, so growth temperatures, let's say around 500 or 600 degrees C, now you're talking about KT values of order about 100. Okay, so these are values that are small compared to the thermal energy. So is this really enough to seed epitaxy? And then if you ask the question, well, if there are also defects, which are probably even larger fluctuations than this, would the defects dominate the growth mechanism? And the reason why we're particularly keyed into these defects is the fact that we don't expect the graphene substrate to be as clean and long-range defect-free as the ideal case would lead you to believe. So everything here, be the DFT calculation, is based upon this picture where you have graphene on top, and a substrate like gallium antimonide, making this perfect interface. In reality, the interface probably looks something more like this, with a native oxide in between. And the reason why is that it's actually not possible to grow graphene directly on 3,5 semiconductor substrates, simply because the required growth temperatures of graphene are way too hot. The substrate would decompose. You need a temperature of about 900 to 1,000 degrees C to grow graphene by typical CVD techniques. But gallium antimonide would decompose if you bring it above about 600 degrees C. So practically, the way you actually make these graphene substrate interfaces is that you grow graphene onto some other substrate, some sacrificial substrate, and then you layer transfer it. So the commonly used process is you layer transfer it through some etch and basically some scooping procedure out of water. And if you're scooping it out of water or out of HCl, if this oxide removal from the HCl is imperfect, then you have to deal with the presence of these interfacial oxides. And you have to ask the question, well, what does that do to the growth mechanism? So we'll pose the question, how do these defects and the interfacial oxides that we expect to be present affect the growth mechanism? So the way we probe this question is that we use surface sensitive tools. So we couple our MBE capabilities for synthesis directly with surface sensitive photoemission spectroscopy. And we use that to measure the chemical state of the sample immediately before under realistic growth conditions. Okay, so if we do that sort of experiment, so this is sort of an example. This is what it actually looks like in real life in my lab. So this is where our MBE system is located. This chamber circled right here is a combination XPS, so photoemission spectroscopy chamber and scanning tunneling microscopy. And since these systems are connected to one another through an ultra high vacuum manifold, we can do measurements directly on the samples without breaking vacuum. So in other words, we can assure that we have measurements on a clean sample surface that is representative of what it looks like in a growth environment. So if we do that measurement, here's what it looks like. So in this set of measurements, we're tracking the intensity of the antimony 3D and oxygen 1s core levels as a function of annealing a sample that looks like this. So 350 degrees C is just a light anneal to desorb any surface contaminants on the that might reside on the surface after transfer. And what you see here are intensity from both an antimony core level, these 3Ds, but also you see a strong oxygen 1s component, indicating that there indeed exists in some sort of interfacial oxide. Okay, you can anneal the sample, and that we anneal it because that's the typical way that you'd remove oxides from a substrate. So as you anneal the sample, sure enough, you can decrease the intensity of this oxygen 1s compared to the antimony 3D. So you can clean it up, right? You can remove some of the interfacial oxides, but the key thing is that the interfacial oxides are present as a result of this transfer process. So then you can ask the question, well, how do these interfacial oxides actually desorb? How does this oxide trapped at this interface actually get out? Okay, and the way we think this happens is by essentially poking holes in the graphene that was originally nearly pinhole free. So at 350 degrees C, this is after the very light anneal. This is before any major native oxide desorption. You can anneal to 450 degrees C. This is sort of the start of some interfacial oxide desorption. We can tell that based upon a sharpening of the specular reflection in our diffraction patterns. And if you go all the way up to 540 degrees C, which is above the native oxide desorption temperature, you can start seeing these pinholes in the sample. Okay. You can also tell the native oxide is desorbing because we start seeing crystalline reflections in the diffraction pattern. Okay, so there are pinholes that formed. Some of them are quite large, on the order of hundreds of nanometers in diameter, and some of them are a bit smaller that you can see at AFM length scales that are about a handful of nanometers to about 10 nanometers in diameter. Okay. As further proof that we're opening up some pinholes, you can do Raman spectroscopy, which will be sensitive if you analyze this D peak in Raman, this D peak in Raman is associated with defects in the graphene. And as a function of annealing at 350 degrees C, things look nice and clean. But as you start annealing to 450 and then 540 degrees C, this is where the native oxides are coming off. This D peak indicates the presence of a lot of graphene defects, and we can observe them directly based on SEM and atomic force microscopy. So there are pinholes. What does that pinhole do to the growth mechanism? And so now what we do is we take our sample that has pinholes, we grow gallium antimonide on top and ask the question, well, where does the gallium antimonide going? And we measure by atomic force microscopy and scanning electron microscopy. And what we find is that predominantly the gallium antimonide seems to be growing inside the pinholes that have opened up. Okay, we can observe that after half a monolayer and 2 monolayers of growth. Okay, at this point, at 2 monolayers of growth, basically all the pinholes have filled up. You can continue growing, and with additional several monolayers to sort of nanometers levels of growth, basically what you have is the start of sort of a lateral overgrowth, as indicated by these sort of mushroom capped shapes. And if you grow out to on the order of several hundred monolayers, you can get full coalescence of these little lateral epitaxy points. So even though we had pinholes to start, we could, because of the very fast surface diffusion on top of graphene, we can recover that a surface that is fully coalesced and looks very, very smooth by atomic force microscopy. We can see atomic step edges here, and the electron diffraction patterns are also highly ordered, so ordered that we can see a very well ordered surface reconstruction. Okay. Despite the fact that we know we have pinholes, we can still exfoliate these samples, right? So here's an example of that exfoliation process. Here's the sample. Here's the membrane that we've now exfoliated from that substrate. We can do X-ray diffraction to confirm that we've exfoliated single crystalline membrane. And we can look at scanning electron microscopy of both the substrate side and the underside of the membrane after exfoliation. So there are pinholes, yes, but the pinholes are small enough that it doesn't long range impede the ability to exfoliate. Okay, so now you can ask the question, well, why is pinhole epitaxy, why is the seated lateral epitaxy the dominant mechanism for the growth in this case? And we think the basic answer is that, well, graphene is highly inert, and graphene has very, very fast surface diffusion. Okay, so the basic criteria you can think about is if there's very fast surface diffusion, what is the characteristic surface diffusion length compared to the average spacing L between defects, right? If the average surface diffusion length is much larger than the average spacing between defects, then essentially all the add atoms can find their low energy bonding sites, and a seated lateral epitaxy mechanism is what you'd expect. So again, the microscopic picture is you have these pinholes that are created by oxide desorption. You have add atoms that are coming down on the surface. Surface diffusion is very fast. So as long as its diffusion length is large compared to the spacing between defects, right? These add atoms can find their low energy, their energetically preferred sites for bonding. And on this sort of surface, the corrugation on top of the graphene, on clean graphene regions, is only sort of on the order of sort of tens of MeV, whereas the sites for direct bonding to the substrate where there are pinholes, those are sites for making direct chemical bonds. Chemical bonds have energy scales on the order of EV. So basically, if this add atom can find these low energy sites, these sites for direct epitaxy, they will. And then because surface diffusion lengths are so long, once you have nucleation in one of these sites, then you have a sort of a lateral overgrowth mechanism. Okay, so you can do further tests of this idea and show that if you take a clean graphene on substrate surface and actually intentionally pattern openings, so let's say you take graphene on top of a germanium substrate, you pattern some openings in the germanium substrate, you can actually achieve highly selective epitaxy in these openings when the spacing between the graphene is tens of microns. So this is further proof that these diffusion lengths and this chemical selectivity for nucleation on graphene terminated surfaces is quite strong. Okay, so what we're doing now is actually asking the question, well, if you wanted to test a true remote epitaxy mechanism, you would need the opposite case. You would need a case where the average spacing between defects now becomes much larger than diffusion length. And we think that graphene grown on germanium is a nice platform to test this. And the reason why is that graphene can be grown directly on a germanium substrate. So now we have a system where we don't even have to do the transfer anymore, and we don't have this complication of interfacial oxides or defects induced by the transfer. And sort of as preliminary data that this is a suitable system, these are AFM height and phase scans of graphene grown on germanium 110. So on the left, I show the height image. We can see nice atomic step edges of the underlying germanium substrate. If you look at the phase contrast in AFM, the phase ends up being a nice map of where the graphene is, because there's a very large elastic modulus difference between graphene and exposed regions of the substrate. And so you can identify a small handful of bright spots that correspond to native pinholes or defects in the graphene. But the key thing to look at is the concentration of these pinholes is very, very small compared to the layered transferred version. So this is only sort of a handful of pinholes over a scan size that's 2 microns by 2 microns. So the characteristic spacing between defects is some number that's on order of microns or several microns. So we think this provides a nice platform for testing possible intrinsic mechanisms for remote epitaxy, where you really require a clean system in order to do that test. Okay, so stay tuned, and hopefully I'll, if I have a chance to report back, I'll be able to share some of our progress in that direction. Okay, last topic with the last few minutes will be this concept of using graphene as essentially a properties-selective diffusion barrier, where ultimately what we'd like to do is be able to grow a half metallic Heuslers film on a semiconductor substrate for spintronics applications. Okay, and the basic problem is that we would like to be able to grow a sample that looks like this, that has very, very well, nearly atomically controlled interfaces between two different materials. And this is a very old example of a superlattice structure that consists of alternating layers of two semiconductors, aluminum arsenide and gallium arsenide, with these nice interfaces between them. Okay, it turns out that this works well, but it's not universal. It's not universal, right? If you were to do a simple thing like try to put down a layer of titanium on top of silicon, you'd actually form these materials are highly reactive with one another. There's large interdiffusion, so you'd actually form this titanium silicide phase. This is somewhat of a universal problem for lots of metals grown on top of semiconductors. Okay. So what we think the graphene can do is basically make us a property-selective diffusion barrier. By putting a sheet of graphene in between that acts as a diffusion barrier, but because it's atomically thin, ideally it would be nearly as close to transparent as possible to charges and spins. And in principle, it might be possible, as we've shown, to grow an epitaxial film where you have single crystalline registry between the Heusler film and the semiconductor substrate, because the graphene is so thin. And that could be dictated either by the idealized remote epitaxy picture, or it may be dictated by this growth through the pinholes in this seated lateral epitaxy mechanism. But before we can really pursue some of these ideas, we first need to understand some of the practical aspects. One of those aspects being, for most substrates, you have to do a transfer. And because there's a transfer, there's often some concentration of pinholes in the graphene. So as a first test, we'd like to quantify what is the effect of those transfer-induced pinholes on the efficacy of graphene as a solid-state diffusion barrier. So the way we're going to test this is we're going to test two graphene systems. one system, we're going to start off with the cleanest possible graphene on semiconductor we can think of, which is graphene that's grown by CVD directly on germanium, no transfer involved. The second system we'll test is where you have graphene grown on one substrate and then transferred to another substrate where you induce some concentration of defects. And again, we do this because it's not universally possible to grow graphene on any arbitrary substrate. So we have to understand what is the effect of some concentration of pinholes on graphene's efficacy as a diffusion barrier. So to test this, what we did was we grew this transition metal manganese on top of these different preparations of graphene. So we grew manganese on our cleanest version of graphene, where we have this graphene that's directly grown on the germanium substrate. We grew manganese on top of the transferred version, where there's some concentration of pinholes, and then we'll compare it against the control of manganese grown directly on the substrate, no graphene at all. And what we do is the measurement is photoemission spectroscopy. So monochromated light coming in, we kick out a photoelectron, we measure the energy of that photoelectron, and then track the intensity of that core level as a function of annealing conditions, going from sort of the as-grown condition and slowly stepping up the anneal temperatures all the way up to 500 degrees C without breaking vacuum. And so if we do this experiment on the control sample with no graphene, for which you expect lots of diffusion, what we find is that sure enough, as you anneal the sample, there is a very dramatic decrease in the surface manganese intensity or surface manganese composition, as you expect from manganese driving into the sample. If you do the same measurement on transferred graphene, you do see basically a decrease of the surface manganese composition. It's not quite as drastic as the control case. And if we do this on our cleanest possible graphene sample, the decay is suppressed. We can start to quantify that by just looking in the relative changes in the manganese 2p core level as a function of anneal temperature. So again, this is the same trend I described. The control case with no graphene, a very drastic drop in the surface manganese composition. Transferred graphene does a little better, suppresses that drop, and the directly grown clean graphene does the best. We can compare that to a simple 1D diffusion model, where you have a Gaussian diffusion concentration profile that's characterized by some diffusion length. From the comparison of this model, we can extract characteristic diffusion lengths after certain anneal temperatures, and we can then come out with an experimentally derived plot of the diffusivity as a function of temperature based upon our XPS measurements. And what we find is that sure enough, the case without the graphene has the very highest diffusion coefficient of manganese into germanium. And for these different preparations of graphene on germanium, the transferred graphene lowers the diffusion coefficient and the direct graphene suppresses diffusion even further. There's a bit more analysis to be done in terms of sort of understanding what the energetics are. We can extract energies for these different diffusion processes. It's a little bit early to say exactly what they mean quantitatively, because I think we need a little more data points, but at least we're sort of establishing the first quantitative understanding of diffusion across these graphene diffusion barriers and the effects of these transfer-induced defects. And finally, just to show you that this approach is stepping in the right direction, right? Even though this transferred graphene is imperfect, it's not as good as a diffusion barrier as this direct graphene case. We show that we can use it to grow certain kinds of Heusler films that we could not grow by direct epitaxy. So if you try to grow this compound gadolinium gold germanium, and if you try to grow it directly on gallium antimonide without the graphene, this blue curve is the X-ray diffraction pattern you would come out with. Okay, so the peaks that we would like to see if we had grown Heusler phase gadolinium gold and germanium are exactly where these shaded colors are, but instead we see a whole bunch of parasitic phases that are in orientations that are marked by these diamonds. If instead you do the version that has graphene in between, now we can actually stabilize the correct phase. There are still some parasitic orientations we're trying to work out, but at least this general approach seems to provide us access and an ability to stabilize some chemically incompatible interfaces that are not possible by a direct epitaxy approach. Okay, so that's everything I wanted to share today. So what I've told you about in the first part of the talk is how we use these graphene-based epitaxy approaches to make new forms of freestanding membranes. And by doing that, we can subject quantum materials to very interesting strain states that you can't do in conventional geometries. And we think we have a nice demonstration of flexomagnetic coupling in a real material. Second part of the talk, I gave you some insights into our atomic level understanding for how this growth process on graphene works. We think that in most experimental cases, it's not these idealized remote interactions that are dominating the growth, but rather it's actually these pinhole defects that are seeding a lateral epitaxy growth mode. And this is important as we're thinking about how to apply remote epitaxy-like approaches to new kinds of materials, and also informs, it tells us a little bit about some of the limitations about what you might expect if the growth process requires pinholes. At the same time, we haven't strictly ruled out a pinhole mechanism, so I think there's a lot more work to be done in really understanding opportunities and limitations by this approach in general. And then finally, I gave you some preliminary data about graphene as a solid state diffusion barrier and some outlook as to why this might be essentially a property-selective version. Okay, so let me thank the people who did the work. Dongshui did all the flexomagnetic coupling work. Sebastian has been our graphene synthesis and transfer guru, and he also did this work on the mechanisms of remote epitaxy. Patrick and Lim did a lot of work on the graphene diffusion barriers. Our graphene samples are grown by the group of Mike Arnold. We benefit by a great theory collaboration with Karen Rabe, and I'd like to thank our funding agencies down below. And with that, I'm happy to answer any questions.
Okay, thank you, Jason, for a really beautiful talk. And I'm sure everybody is clapping, although they are muted in this setting. So we have 3 questions that have already come in through the Q&A, but I'll encourage people to continue to add those and type them in the box if they have additional questions. So the first one is, how does the gadolinium platinum antimony in plane lattice parameter match the bulk value, or is the value expected for remote epitaxy on the graphene / sapphire?
Yeah. So the gadolinium platinum antimony actually almost immediately relaxes to its bulk lattice parameter. But you would probably expect that to occur with or without the graphene. And the reason why is that the lattice mismatch between graphene and sapphire, the lattice mismatch between gadolinium platinum antimony and sapphire is already reasonably large. That value is it's a little more than 2%. I think it's 2 point something percent. So that critical thickness is already a pretty small value. It's an interesting set of questions though, right? If you had a system with a smaller mismatch, what is the critical thickness limit in those regimes? And I think that's a question that Jiwan has looked at a little bit. He has a nice paper, I think it's in Nature Nano, looking at different strain relaxation mechanisms when you grow films on graphene, because essentially it's possible to sort of slip across that interface.
Okay. I think our next question is in the same light, but with remote epitaxy, how well lattice match should your film be to the substrate to form the right phase? And would you expect other single layer but thicker van der Waals materials to enable remote epitaxy?
Yeah, so we haven't explored enough. We haven't really been pushing the limits of what sort of mismatch you can get away with. So I can't. I maybe could give you like an intuitive answer. Well, actually, honestly, I don't have a good answer. I think it's an interesting set of questions. I don't have a great answer.
Okay. And do you have any guesses if it has to be graphene or other van der Waals materials might work as well?
Yeah, so I think you can think of it from several perspectives. One perspective is to think about the lattice potential of your 2D transparent material. And from that perspective, graphene might be a nice choice because it's all carbon in the basis. So minimal fluctuations of the graphene's lattice itself. An alternative you can think about might be HBN, but because it's a material with a 2-atom basis, there's some fluctuation between boron and nitrogen sites, and maybe that might interfere with the substrate potential itself. And I think Jiwon's group has done some with HBN, and they've had some limited success growing on top of HBN. But it's certainly not been as exploited from the graphene case. The other thing I think about a bit is possible screening effects, right? Because graphene is a metal, so you could have screening of the potential through metallic graphene. It's a sheet charge on top. And from that perspective, something insulating would be better, right? So from that perspective, maybe HBN is better.
Mm-hmm. So we have a question on something that's actually not on the growth, but going back to your beautiful demonstration of the flexomagnetism. And so the question is, what would it take to definitively demonstrate flexomagnetism? And some suggestions were, would it be DFT modeling of the rippled structure or a specific experimental signature?
Yeah, so we're going after both approaches. I would first caution DFT is hard, or at least a brute force DFT is hard for anything with strain gradients, because at least by brute force you'd be talking about something with a very large unit cell. And I think there's some clever approaches that have been developed for flexoelectricity that might map onto this sort of problem. So I think there's something to be done there, and that's something we've been actually talking with Karen about. From the experimental perspective, if you could make a sample where you directly compare a homogeneous strain state of the same magnitude with something rippled of similar magnitudes, that's what we'd like. So we're actually actively doing that. So with our membranes, you can, instead of making ripples, you can make a little clamp assembly and you pull on it. Okay, so we're looking at that. The other thing to look at is, I guess one thing I kind of glossed over, but it could be a change in the particular type of homogeneous strain might make a difference. So all of our calculations were for biaxial strain, where you're straining equally along the X and Y in plane directions. But maybe the crystal field environment of a uniaxial strained system is different enough such that if we applied that strain in one direction, the answer might be a little bit different. So we're also looking at that. So yeah, I think there are a number of ways you can approach this problem.
Okay, I think that's all the urgent questions that have come in through the Q&A. I'm sorry that Jason isn't here on campus to meet with all of us and have chances to chat with us all today, since I'm sure there's a lot more really exciting conversation and kind of things people would want to know from you. But I'll kind of virtually thank you again, Jason, for the really beautiful talk. It was really our pleasure to be able to host you. And we do hope that you can come visit us at Harvard in person sometime soon.
Yeah, thanks for that invitation. It was great to speak today. And if you have questions, I'm more than happy to follow up by email.
Good. Okay, thank you.